Good. Let's start with the third part of this tutorial, which is about word embeddings. So let's open this one. Well, word embeddings we have already discussed in quite some detail in a previous unit, based on mostly on Word2Vec, on the Word2Vec model and the Gensim library. So you already should know what word embeddings are, how they work, how to train them. But here we have a little bit of a different take on them, also on how to integrate them into some deep learning architecture. And also we have quite a nice theoretical introduction or explanation of what word embeddings are and why we want to use them. So I highly encourage that you read all the text in this notebook very carefully. I think it's quite interesting and should be not so hard to understand. And it also helps you to remind you of the basic concepts like one-hot encodings for words, on bag-of-word encodings for documents or sentences, and what word embeddings are and why they are helpful for representing words and documents. So here in this explanation, they start with the one-hot encodings. The problem with one-hot encodings, as you might already know, is first of all you have very large vectors of dimension of the vocabulary size, with just one in there, and everything else in the vector are zeros, and you don't have any information about the semantics. So every vector is orthogonal to all the other vectors. So you cannot compute any similarity between vectors, between words. And with the word embeddings, then here they first discuss the idea of having dense representations, and those dense representations have dimensions which represent specific features of the words. For example, here they have two words, mathematician and physicist, and say, okay, they might have features like if the thing can run, if it likes coffee, if it majors in physics, and so on, and many other features. So this would be one way how you could build a word embedding manually, if you just think, okay, 100 features that a word has, gender, is it an object or not an object, and so on, and then define the word embeddings yourself manually. But obviously this is not scalable. You cannot define 100 dimensional vectors for hundreds of thousands of words manually. So we want to learn those vectors from the text, as we already did in a previous unit. And by learning those vectors, the feature engineering, it's done by the network itself. So there are no manual features, the feature engineering is done by the algorithm. The features or the dimensions themselves have no clear semantics. They just somehow, without us knowing exactly what the dimensions mean, encode the semantics of the vector, of the words into vectors. And when you have those vectors, you can do similarity operations between vectors, as we have discussed already. Okay, let's have a look on how to use word embeddings in PyTorch. And here it's also about how to train your own embeddings and not just use pre-trained embeddings. In many practical applications or tasks, you would probably start from pre-trained embeddings because they are already trained on large document collections, so they have very good encodings for the words. But maybe then you want to fine-tune those embeddings to your specific domain, or you can even train your embeddings from scratch. as part of the deep learning network. So how do embeddings work in PyTorch? So in this first part, we just include, import the different parts of the library. Then here we set up some simple embedding layer for PyTorch. So first we define which words we have in our vocabulary and which place, which item they are. Hello is on place 0, world is on place 1, and so on. So the index of the words. And then we define an embedding layer. So in PyTorch it's with this nn.embedding. And then you have to tell the embedding layer how many words you have in your vocabulary and how many dimensions you want to have in your embedding vector. So this, as I understand, just creates a random vector. So it starts from a random initialization, and then you can have a look at one of those vectors, which we do here, and we print it, and we see that the vector for hello, for the first word, it's 5 numbers, so as we expected, because we said we want to have 5-dimensional embeddings, but at this stage it's just random numbers because we just created this embedding layer from scratch. Good, and then it goes on here with using some word embeddings to create a simple language model. So as we already have discussed, language models are models which predict the next word on a sequence of input words or input tokens. So there are bigram language models, so where, for example, you have 2 input tokens and then you predict the next word, and so on. Or you have longer sequences of words and predict the next word based on the input sequence. In this example here, we will use the 2 previous words, which is here the context, so the 2 words to the left, and from these we predict the next word. So as input we would have something like when 40, and the model should predict winters, or 40 winters, then the model will predict shell. So we always predict the next word from the previous 2 words. This is the goal in this language model, in this n-gram language model, which we want to create here. So we define the embedding dimensions. So we use a 10-dimensional vector in this example, so very small. In practice you would maybe have a larger one, like 50 dimensions or so, to capture more detailed information about the word. And then we create a training set, which is stored in the variable trigrams, and the training set, it's just iterating over the sentence, which is split into words. So we have here the sentence defined, we split it into single words, then we iterate over these words in the sentence, and we always take 2 words, word I and word I plus 1, and as label, because this is the goal which we want to predict, we put into this training data which we create here, we put the word I plus 2. So we have 2 words in sequence, and the next word is the label which we want to predict. Then when we print those trigrams, the first 3 elements, and go down to the output, we see that the training data now looks like something like this. So this is one training instance when 40, and we want to predict winters. 40 winters as input, or as input data, and we want to predict shell, and so on. So we will probably, from this text here, we're maybe something like 60, 70, I don't know how many words it is, training examples which we created here into this trigrams variable. Okay, then next step is we need to know what is our vocabulary and how big it is. So we just make a set from the words, which is our vocabulary, and then we create this index, which we always need from a word to a number in this way, because PyTorch and all deep learning algorithms, you don't give them words as input, you have to give it numbers as input, so we have to convert it to numbers. Good. Here in the next step we create the Ngram language model class. It always has to be based on the PyTorch module object, and we define two functions, the init function and the forward function. The init function, as the name suggests, it's just for the initialization of the network, and here we define which layers we have in our network. So we define an embedding layer, which is, as we said, has as parameters the size of the vocabulary and the embedding dimensions. Then we have, after the embedding layer, one linear layer, which has as input the output of the embedding layer. So as we know, in the network, the data will basically flow through the different layers. So after the embedding layer, we have the linear layer, and it gets the output of the embedding layer. And as we have two words which is the input to the system, we have two words and then predict the next word given the two words. We have the context size of 2 multiplied by the embedding dimensions, which is the input to this linear layer. And then this linear layer has an output of 128 nodes. And then finally we have a second linear layer where we now project from this 128 nodes to the vocabulary size, because finally, after all, we want to predict words. So which word will be the next one? So we have as many words, as many possibilities as there are words in the vocabulary. Then the next function is the forward function, where we just build the computation graph of a network. So we have the forward function gets the inputs, so the two words basically which we want to predict the next word for. It takes the inputs, puts them into this embedding layer, and this is then saved into embeds into this variable, which we then feed to the linear layer, where we do this linear matrix operation on the vector of embeddings which we created. And we also have some nonlinearity or ReLU function on top of the output of this matrix operation. And then we take this and feed it into the second linear layer to get to our vocabulary size number of predictions for which we can then use in the final step. We apply a softmax function to have the probabilities on those classes which are predicted, and this will return back. Good. Finally, before we can start with the training, we define our loss function, which is here the negative log likelihood loss, and we initialize our model here. So we instantiate our model, and we define which optimizer we will use to update our weights. And one standard one is the stochastic gradient descent optimizer, and we give it a learning rate on how far to step in every optimization step, in every update. Okay, finally, now we have it all set up, we can start with the training. So now here we have 10 epochs for which we train, and as in the last unit, we iterate over the context, which is the input of the system, and the labels, the target, which are in this variable trigrams. Then first we transform the context, the words, into torch tensors, which is done here. So we just take index, so we take the number for the word and then put this into a tensor. So this is our context IDs, which we use later. Then we zero the gradients. This is just a standard thing which we already discussed. Then we apply the model to the inputs and get the probabilities. So in here basically this is all the network operation applied to the input words. We get the probabilities and then we can compare those probabilities to our targets, which we again put here into a tensor. So we put the targets, the labels, so the next word after the two words, into a tensor, compare it to what was predicted by the model, and this is and we apply the loss function. So how far away are the predictions from the labels? And with this we can then call the backward function, which creates the gradients. So it does backpropagation through the network, and finally we can update our network to improve hopefully the quality of the output in the next iterations. Okay, that's the whole training process, and we collect the losses and print them so that we can observe after the training how the loss improved during the training. And yeah, this is what you see here in the last line, that the loss should go down. So it's improving. We are learning to better and better predict the next words. Yeah, what they did not do here, so usually you would have some evaluation on how many words were predicted correctly, or whatever evaluation method you want to use. Or you can just do some random predictions on some input data to see what kind of results you get, if it makes sense or not.